Hello everyone, welcome to my YouTube channel. So in this lecture, I will discuss about the electronics effects on the IR stretching frequency of the different functional group in the organic molecule. So we find that the vibrational frequency a bond depends on its bond strength. Now with the increase in the polarity of the bond strength increases. The electronic factors affect bond strength of different functional group. The carbonate group present in aldehyde, ketones, acid, stars, amide, acid chloride, anhydride. So this group absorbs strongly in the rays of 8550 to 1650 because it large change in the dipole moment. The C6 stretching frequency is sensitive to attached atoms. So C double bond O frequency is of a ketone, which is approximately the middle range of this is usually considered the reference point. So this is the value of the carbon stretching frequency of the different carbon group like anhydride, acid chloride, anhydrous, star, aldehyde, ketones, carboxylic acid, and amides. So first I will discuss about the aldehydes and ketones. So for simple aldehydes and ketones, the stretching vibration of the carbonyl group give rise a strong and distinct infrared absorption at 1790 to 1740. The strong absorption at 1715 centimeter inverse that correspond to the carbonyl frequency group is highly characteristic, thus open enable to chemists that distinguish the peak in the potentiality confusing situation. For instance, so to some extent, C double bond O, C double bond O, C double bond also in the same region of the influence spectrum. As the dipole moment of this function is increased on stretching, the result is a strong absorption. A carbonyl group can consider to the resonance hybrid of the following two canonical forms. So here, these two canonical forms of the carbonyl group, they have delta positive charge on the carbon atom or delta negative charge on the oxygen atom. So now ketones are absorbed at lower frequency than the aldehyde because of their additional alkyl group, who is the electron donating and the supply electron to CC double bond. The electron releasing effect weakens the CC bond in the ketones, thus the lower the force constant. So another term, since the alkyl substitute stabilize the carbocation tract of the ionic contributor, its contribution hybrid increase. As a result, ketone carbonyls have the slightly lower stretching frequency compared to aldehyde. So that means that this carbonyl group has these two resonance forms. So when the in the keto group, when the two alkyl group is present, so that is the in this case the ketone this resonance is to some extent stabilized. So here slightly the carbon oxygen double bond character is reduced. So that's why the carbon oxygen stretching frequency in ketones is slightly lower compared to the aldehyde. So aldehyde show very sharp strong band of the carbonyl that appears in the 1740 to 1725 centimeter for simple aliphatic aldehyde. So a very important doublet can be observed in the CH stage region of aldehyde. The CH stretching frequency near 2850 to 2750. So the presence of this doublet allows aldehyde to distinguish from other carbonyl containing compound. So it is easier to see the band at the lower frequency because it's not hidden by the usual CH bond from the alkyl chain. These two peaks appear in the coupling between the fundamental CH stretching frequency vibration and fast overtone of the CH bending vibration, which is referred as the Fermi resonance. So that means in the carbonyl, in the aldehyde, the carbonyl stretching frequency is around 1740 to 1725, and here also the CH stretching frequency is observed. This is two tablet. So this is lower compared to the normal alkene CH stretching frequency. So that is easily resolvable from this. So this is the stretching frequency of this carbonyl moiety. So this is the CO stretching frequency, and this is the aldehyde stretching frequency of this carbonyl group. So four factors are known to be part of the carbon stretching frequency. So first one, the conjugation with a double bond or a benzene ring lower the stretching frequency. The where normal ketones show stretching frequency vibration at 1715. A ketone that is conjugated with CC double bond absorbed at lower frequency near 1675 to 1680. The 30 to 40 centimeter inverse decrease in frequency illustrated by the following example. The stretching frequency of conjugated double bond is allowed lowered. The cinnamaldehyde showed the extent of conjugation further lower the absorption frequency, not to the same degree. So here, when the first factor is the conjugation with the double bond or the phenyl ring. So here this is a without conjugated keto product, the carbon group, and here a conjugated carbon product. So due to the conjugation, the carbon oxygen double bond character is somehow reduced. So here due to this, the carbon oxygen stretching frequency is lowered compared to the normal stretching frequency. But in this example, here when the carbonyl group at position beta and here is the alpha position. So here for the alpha beta position, there is no conjugation with this phenyl ring, but in the alpha position where it is a conjugation with the phenyl ring. So that's why here the infrared stretching frequency for this carbonyl group is lower compared to the this one. And also in the case of the cinnamaldehyde, where the carbon double bond is present. So here due to this conjugation of the carbon double bond with this carbonyl, the slightly single bond character. So here the carbon oxygen frequency is lower in this compound. So this reason for our the conjugation extend the dipolar character of the carbonyl group of the double bond, so that the beta carbon atoms share the positive character of the carbonyl atom carbon. This is resonance lengthen the CO bond distance and illustrated by the following resonance, which is also suggests that the carbonyl bond has slightly more single bond character than the unconjugation function. So here when this is the canonical structure of the conjugated CO double bond. So here this is the canonical structure. So here there is a carbon oxygen double bond has a slightly single bond character. So both of bond energy of the conjugated CO bond is correspondingly reduced, and this result the stretching frequency, thus the following stretching frequency of this here for this compound, this carbon stretching frequency is that region, but when it is the aldehyde group, the carbon is very slightly lower. So let us consider the following example. Here the carbon stretching frequency for this molecule is slightly higher compared to this. So this is the reason, because here this is a bicyclic compound. Here this is highly strained compound. So here this highly due to the highly steric nature, this carbonyl the CO double bond is out of plane from this phenyl from this aromatic ring. So it is not in, with the conjugation with this aromatic ring. So that's why it's stretching frequency is slightly high compared to this. And for this case, there is a long chain alkyl. So here the CO double bond is slightly conjugated with this aromatic ring. So that's why for this case the conjugation is not hampered. So here the carbonyl stretching frequency is slightly lower compared to this. So in this case, the carbon group would not be conjugated with the carbon double bond. But in case of second compound, the carbonyl group is the plane of the ring, because the higher ring side, that's the carbonyl conjugation of carbonyl group. So in addition to this conjugation, often nucleus has got aromaticity. Obviously, this conjugated the double bond character reduce the double carbon reduced, and the result is a lower stretching frequency. So next factor is the changing the alkyl substitute of ketone for electron withdrawing or releasing group may shift the carbonyl stretching frequency up or down. So next factor is the electron donating effect. So the following example, so the implies a strongly electron withdrawing group and the conjugated electron donating group. So in this case, here the alkyl substituted, here trichloro substituted. For the trichloro substituted, here the carbon frequency slightly higher is higher compared to this alkyl substitute, because here this strong electron withdrawing group which stabilize the which strengthens the CO double bond character compared to this. So here that's why the carbon stretching frequency is increased. So also in this case, here no substitution, or here the substitution. So this has a higher stretching frequency compared to this, because here the electron donating group stabilize the conjugation with this carbonyl group. So that's why the carbonyl oxygen double bond character is some reduced for this case. So that's why here the stretching frequency is decreased. So electron donating substitution on the carbonyl group stabilize the ionic resonance contributor and increase the single bond character of the CC bond, and the stretching frequency therefore decrease. The electron withdrawing groups have an opposite influence, increase the stretching frequency of the carbonyl groups. So this is the canonical form. So here this the lone pair of the oxygen is stabilized. So this so here the carbon oxygen single bond character, that's why the carbon frequency decrease. But here the carbon frequency increase due to the electron withdrawing nature of the group. So in case of alpha haloketone, when the carbon next to the carbon next to the carbon substitute the chlorine, such as this one, the carbonyl band shifts to higher frequency. The electron withdrawing effect destabilizes the dipolar structure of the carbonyl group, thus diminishes the contribution of dipolar structure resonance hybrid of the carbonyl group. As a result, double bond character carbonyl group will increase, and therefore the force constant of the carbonyl group increase. This leads to the increase in the absorption frequency, which is hold for the all carbonyl compound. So electron withdrawing group, it also decrease the dipolar structure, decrease the stability of the dipolar structure. So that's why the carbonyl stretching frequency increase for the electron withdrawing substituted carbonyl compound. However, a normal haloketone shows two bands at CO is 125. This can consider rotational isomer. So here this is two isomer A and B. Change the conformation A, CO faces the dipolar repulsion, while Cl bond due to the high electron of the oxygen and chlorine atom, thus the normal resonance of CO bond is hampered and CO is a higher double band character. So for A, the band separated is 745, whereas in the conformation this, so in this case the this CO and Cl is in Gauss is in sin orientation. So here the electron repulsion between the Cl and CO double bond. So that's why the CO double bond character increase. So it has higher resonance character. But in case of B, the CO and Cl bond is in the anti, thus the dipolar repulsion between them elevated, and the result CO band appear as a normal region 725 for the conformation B. The information of this here. So for the B, the Cl and the C double bond O here in the anti-conformation. So here the no dipolar repulsion. So here the normal region comes, the carbon frequency came at the normal region. Information thus can establish the structure of the ring system. The following example is the axial and the equatorial. So equatorial case, these two in the same direction. So here dipolar repulsion. So here it is a higher, slightly higher compared to this, because in this case it is anti-conformation. So it is a trans conformation. So there is no dipolar repulsion. So here the stretching frequency is lower. So that's third factor is the incorporation of the carbon group small ring size. So ring incorporation of the carbon group small ring raises the stretching frequency in compared to the cyclohexanone. The increase in the frequency range 30 to 40 centimeter inverse. The 5-member ring to 50 to 60 inverse, for 4-member ring nearly 130 and 3-member ring 150. So under ideal condition of the carbon atom of the carbonyl group, essentially the sp2 hybridized, which implies their bond angle 120, and CO sigma bond as the 30% is character. Now we know that the sp hybridization bond angle is 180, sp2 hybridization bond angle is 120, sp3 for 109.28. Thus, it is reasonable to say that P character of CC double bond in the ring increases and the decrease in the. So here from this hybridization we can tell that when increase in the P character, there is a decrease in the bond angle. So when the P character is for the small ring, for upon this to this, the ring size is decreased. So here the P character is more used for the formation of ring CC bond. So in this, that's why the decrease in the bond angle. So if group incorporated a small ring, the CC or double bond character reduced to one derivative. When this happened, the CC bond of the ring assumes to greater P character, and CO sigma bond has a corresponding greater S character. So the double bond of the carbonyl group is therefore shorter and stronger, exhibit higher stretching frequency. So again, there another example, a di-butyl ketone. We have the following observation. This is the lower stretching frequency compared to this due to the more electron donating group substituted. Here the CO bond angle is higher than 120. Thus lower P character is used for the formation of CO bond. First and lower S character is used for the formation of CO bond, C double bond. thus this will increase the decrease the force concentration of C double bond. Thus, the staging frequency of C double bond, the target frequency is decreased. So the above shift also isomer in the presence of the previous conjugative lowering the staging frequency. So here these and these here this case the conjugation of the double bond of the carbonyl group. So here the staging frequency is decreased due to the conjugation. Here the unconjugated ketone the no conjugation occur. So here the staging frequency is higher. Also in this case this has the higher staging frequency compared to this here because here this carbonyl staging is more closer to the benzene ring. So here the conjugation is occurred, but this carbonyl is far away from the benzene ring. So this case the conjugation is not occurred. So that's why this has a higher staging frequency compared to this. So the unconjugated diketones that have the two carbonyl group adjacent to each other. So the one strong adjacent peak 1716 centimeter inverse. If the two carbonyl groups are conjugated with the aromatic rings, the absorption is shifted to a lower frequency value of 1680. In the latter case, the narrowly spaced doublet rather than a single peak may arrive with the symmetric and asymmetric adjacent. So here the diketo with the phenyl ring in the alkyl group, the phenyl ring in the here the conjugation is occurred. So that's why you have the lower staging frequency compared to the this. So diketones with the carbonyl group located to 1 and 3 with respect to each other may yield a more complicated pattern than those of the observed most ketone. Thus, the beta diketones can exhibit tautomerism with the equilibrium mixture of enol and ketone. Since the many beta ketones contain large amount of enol, one carbonyl peaks of both enol and tautomerism may be observed. So here it is ketotautomer, here is the enolautomer. So the carbonyl group, the enol form appearing in 16220, that is subsequently shifted and identified and combined the normal ketone. So the shift is result of the internal hydrogen bonding. The hydrogen bonding of the carbonyl group extends the CO1 length and lower the staging force constant, resulting in lowering the carbon staging frequency. So detonants, however, also contribute to lowering the carbon staging in enol form. This effect induces single bond character in the enol form. The weak OH stage also observed from enol form. Since this keto form is also present, doublet of the asymmetric staging frequency is observed for two carbonyl groups. The relative intensity of enol ketone carbonyl group is dependent on the percentage of equilibrium. Hydrogen bonded carbonyl groups in enol form are open observed region. So these keto form is generally as a doublet in the region of 170 to 169. So when by the IR spectroscopy, we can identify the keto and tautomerism percentage. So here in the keto form, obviously CC double bond character is present, but in case of enol form, the CO double bond is to some extended gain the single bond character. There is the hydrogen bonding with this hydroxyl group. So here the staging frequency is lower compared to this. Here also the OH staging frequency observed, which is come as this region. So that and the intensity of this the staging frequency also depend on the percentage of the keto and enol tautomerism. So next we will discuss about the carboxylic acid. So the carboxylic acid exists in a monomeric form only in very dilute solution. It absorbs around 160 slightly higher frequency comparison to the commonly carbonyl group. This is because the electron element tend to draw the electron between the carbon and oxygen atom. This is electron, so the CC bond becomes somewhat stronger. Obviously, the oxygen is more electron in the carbon. This effect dominates in case of carboxylic acid in case of CO staging frequency. So in the CO staging frequency is normally the CO staging frequency is higher compared to the later ketone due to the because the electron withdrawing nature of the oxygen atom that is attached to the alpha carbon that will withdraw the electron from the carbon center. So that's why the CO bond is C double bond O is somehow extend the stronger. So that's why the carbonic staging frequency increases. However, the acid in conjugation solution form neat liquid when the solid state tend to dimerize by hydrogen bonding. So dimerization weakens the CO bond and lower the staging force constant K, resulting in the lowering of the staging frequency. So carboxylic acid so very strong than for the CO group that appear at the assembly. For example, the levity carboxyl dimeric form. This band shifted to the lower frequency range with the conjugation of CC double bond or phenyl group. The most characteristic feature of the sector carboxylic acid is the extremely lower OH absorption occurring in the region of 3402 to 2400. This band is attributed to strong hydrogen bonding within the dimer. The absorption open occurs in the stage stretching field violation that occur in the same region. If these broadened hydrogen bonded band is present together with the proper CO absorption value, the carboxyl osmotically certainly are anticated. So this is the staging frequency of this acid group. So here this is a strong absorption at the OH that in this 3400 region, and here the CO staging frequency in this 1715 region. So the carbon staging absorption which may occur at 7 for the dimer is usually broader, more intense than the presence in the aldehyde or ketone. For most acids, when the acid is diluted with the solvent, the CO absorption between increases. So for the monomer, however, the monomer is often not often seen experimentally since it is usually run to the spectrum as a neat liquid. So it's removed the dimer even in the dilute solution. So halogenation of the alpha carbon related to the acid group leads to increase the CO stretching frequency because of the electron withdrawing nature. Electron withdrawing effect of halogen atom removes the electron from the carbon of the CO double bond. This removal is compensated by the tightening the pi bond, which increase the force constant leads to the increase in the absorption frequency. Next, we will discuss about the ester and lactose. So esters show very strong band for the CO group that appears in the range of 750 to 735 for the simple aliphatic ester, which is much higher than the CO in the carbonyl compound. This is simply because the fact that so electronegativity of the oxygen atom of the carbon makes a minus I effect, where two more dominating about this plus R effect. So ester has the high stretching frequency compared to the aldehyde because due to the electron withdrawing nature of this oxygen atom that will withdraw the electron from the adjacent carbon center that will strengthen the CO double bond. So that's why the CO double bond of ester is comparatively high region compared to the aldehyde or ketone. So the staging frequency is often shifted by 50 to 25 centichambers to lower frequency with the alpha beta unsaturation or allyl substitution. This is because of the conjugation effect. The introduction of CO bond adjacent to the carbonyl group resulted in delocation of pi electrons, the C double bond. This conjugation increase the single bond character of the C double bond and CC double bond in the resonance hybrid, and hence the lower the force constant, resulting in the lower the frequency of the carbonyl double bond absorption. So in the case of ester, when the double bond is conjugated with this carbonyl group, that case the stretching frequency is lower. So conjugation with the triple bond also show the effect, denial the introduction of alpha beta double bond in a carbonyl group resulted in the 25 to 45 centimeters lowering of the stage stretching frequency from the base value given. A similar lowering occurs when the adjacent aryl group is introduced. In addition, CO double bond acids from its normal value have lower frequency value that of the CO absorption greatly intensified. So in this example, so here no CC double bond conjugation, so that's why it is a high region value. And here also the CC double bond, here the benzene is conjugated with this ester. So here the stretching frequency is slightly lower compared to this one. So that's why the upon the conjugation of the double bond, the stretching frequency is lower. The spectrum of both methyl and methacrylate and methyl benzoate. So the CC double bond as a seed from the position of normal ester by ethyl butyrate. Also notice that the C double bond C absorption band at 1630 is methyl has been intensified over that obtained in non-conjugate double bond. Open to closely spaced CO absorption peaks are observed from this conjugation, resulting in the two possible conformers. Yes, so here for this case, here two conformers. So here two possible. So S confirmation absorb the higher frequency than the S turn confirmation, because so here for these two conformation the S C's has a higher stretching frequency compared to the S turn because in the end S terms there is a favorable structure for the conjugation with the carbon carbon double bond and carbon carbon single bond, but for the cis transformer there is no favorable conjugation structure for the conjugation of the carbon carbon double bond and the carbon oxygen double bond. So that's why the cis conformer has the higher stretching frequency compared to the trans. So in cis conformer, two pi bonds are in a repulsive orientation and constantly they have tried to remain apart and thereby conjugation hindered. Thus we have the above observation. So the conjugation involves the single bond oxygen in the vinyl ester and phenyl ester shifted the CO vibration to the higher frequency. Apparently, the conjugation interference with the possible resonance to carbonyl leading to the increased absorption frequency. So here when the stretching double bond character double bond introduced in the oxygen carbon, so that's why in this case this resonance form and in this case the stretching frequency increases. The phase spectrum of the vinyl acetate CC double CO double bond appears at 176 to an increase of 25 centimeters of the normal star. This substitution of the allyl group on the oxygen also gives a similar pattern. So here the ethyl butyrate had lower stretching frequency than this. So here the carbon oxygen CC double bond and phenyl conjugated with this oxygen. So here no conjugation effect with this CO carbonyl stretching frequency. That's why the carbonyl stretching frequency increase. So in general, effect of the alpha beta oxygen or aryl substitution and the conjugation with the oxygen of CO bond. So here the normal star when this there is a alpha beta unsaturation with this conjugation with oxygen. So that's when the stretching frequency is lower compared to the normal star, and when the oxygen when the oxygen atom is substituted. So alpha beta aryl conjugation the frequency lower, and when the conjugation with the oxygen atom, that case the stretching frequency increased from the normal one. Let's let's take a look cosmo aspect of lactons. The unstained 6-member cyclic star alpha value lacton observed about the same value as the non-cyclic star because the increase in interested alpha butyl lacton observed percentage higher than this. So here this one has the high stretching frequency to this because here the ring stem there is a small ring size, more S character on the CO double bond compared to this. So here more stretching frequency in this region. So because CC vibration are shifted to the higher frequency and decrease the ring size because of the smaller ring size, use of the more P character to make CC bond for the requested small angle and remove of the P character from the sigma bond CO double bond group part. It gives more S character, the strengthening the double bond and the corresponding increase the absorption frequencies increase. So the effect of the ring size alpha beta unsaturation conjugation with the oxygen on the CO vibration of the lacton may be depicted. So here when the alpha beta conjugation, so that case the stretching frequency lower compared to this, and when the conjugation with the oxygen, that case the stretching frequency increase. Same case for this one when the alpha beta unsaturation there is lowering the stretching frequency, and when this same conjugation with the oxygen atom, that case the increase in the stretching frequency. So beta keto esters are often class of compound which include automorphism like that of the beta diketones. Now the less evidence exists in the anal form because the beta keto ester do not analyze to great extent. Beta keto ester exhibits strong intensity doublet of 2 carbonyl 170 to 1740 in the keto recomer, presumably for the keto and the ester CO groups. Evidence for the weak intensity of the C1 in the electrotomer appears at 1650 because of the low concentration of electrotomer. One generally cannot observe the broad wastage that observed from the beta diketone. So here beta keto ester, the enol form is not to some extent stabilized compared to the beta diketones. It is more only in the keto form. So that's why the only to some extent CO double one CO stretching vibration lower. The two bands appear for CO stretching vibration in the star in the range of generally the CO stage next to the carbonyl group of a star is one of the strong and broadest band in the spectrum, easily sufficient to found at least one very strong and broad absorption to help the identify the compound in star. So next we will discuss about the amide. So amides show a very strong band of CO group that appear in the range of 1680 to 1660, which is lower than a simple carbonyl group or diketone. This is because amide has a lower CO stretching frequency compared to the normal aldehyde ketone. This is because in the adjacent nitrogen has a electron donating nature that will stabilize this bond where the carbon oxygen stretching frequency to bond length has slightly the single bond character. That's why it is stretching frequency lower. So obviously here the unpaired electron on nitrogen atom in conjugation with the carbonyl group, since the nitrogen is less electronegative, it can more easily accompany a positive charge, resulting in the increase the single bond character of the CO group and thus lowering the CO absorption frequency. In addition, the NH state is often in the range of 1.45. A pair of fairly strong NH stretching band appears about the for primary amide. The monosubstituted amide shows only one band in the same region. NH banding occur at this region for primary and secondary amide. So cyclic amide give the extent decreasing CO stretching frequency but decrease. So here also with the decrease in the ring size, the CO stretching frequency also increase. Next, we will discuss about the acid chloride and anhydride. So acid chloride and anhydride are the most common functional groups that have a CO appearing at high stretching frequency. Acid chloride show very strong band at CO group at around 180 to 1.5 for aliphatic acid chloride. In the acid chloride, highly electronegativity halogen atom strengthen the CO bond so that enhances the inductive effect and shift the frequency to value higher than the found in ester. So we have the following observation. But due to the electronegative nature, the stretching frequency is slightly increased. The conjugated acid plus such as benzoyl chloride observe at the lower stretching frequency, which some aromatic acid chloride may observe the another strong band open the lowering stretching frequency of the CC bond, which makes the CO bond appear as a doublet. So this band which appear in the spectrum of the benzoyl chloride 1730 is probably the Fermi resonance band orienting from the interaction of CO hydrogen, while the overtone strong band there is CO stretching open here at the range of 900 to 800 centimeter inverse. So anhydride are likewise shifted the frequency higher than the found in the ester because of the minus I effect of electronegative oxygen atom in more prominent over this plus R effect. Anhydride show the strong band of CO groups. Simple alkyl sulfate anhydride generally gives band at 1.820 to 1.5 centimeter. Anhydrides give two absorption band that are due to symmetric with the antisymmetric stretching in hydrogen. So conjugation shifts the absorption to a lower frequency, while cyclization shifts the absorption to a higher frequency. Simple 5-member ring anhydrides have the bands at 1860 to 1780. Next, we will discuss about the hydrogen bonding effect. So the hydrogen bonding appears in the molecule when each atom is attached with a highly electronegative element, ON or halogen. Now, the alcoholic or phenolic OH group participate in H bonding. Obviously, H bonding leads to the decrease the strength rate of H bond. So upon the hydrogen bonding, the stretching frequency lower compared to the normal non-hydrogen bonding. So here, mu bar xi will decrease due to the hydrogen bonding. So when alcohol or phenols are determined in the pure liquid things, as a common practice, a broad OH stretching frequency obtained for intermolecular hydrogen bonding range of 0.000 to 370. As the alcohol is diluted with the carbon tetrachloride, a sharp free OH stretching band appears on 330 to lead to the brand. So when the solution is further diluted, the broad intermolecular hydrogen bonding is reduced considerably, leaving as a major band of free OH stretching frequency. So the intermolecular hydrogen bonding weakens the OH bond, thereby shifting the band to the lower frequency. Again, the intramolecular hydrogen bonding present in the orthocarbonyl substituted phenol usually shift the broad OH to the lower stretching frequency. For example, the OH bond in the center at about 3200 centimeter in the neat spectrum of the methyl salicylate, while the OH band the normal phenol are centered at about 3350. So in addition, hydrogen bonding to the carbonyl group lengthens the CO bond, C double bond O, and lowers the stretching force constant of K, resulting in a lowering of the absorption frequency. Thus, the lowering the ester of stay frequency in the methyl salicylate caused by the intermolecular hydrogen bonding. So here, due to the intramolecular hydrogen bonding, the CO stretching frequency is lower. So obviously, with the increase the dilution, we can destroy the intermolecular hydrogen bonding, but in case of increase the dilution, we cannot destroy the intermolecular hydrogen bonding. So the intermolecular hydrogen bonding does not change in the position significantly when the high dilution because the internal bonding is not altered by changing the concentration. Thus, the IR study at the defined direction can utilize to detect the presence of intramolecular or the intermolecular hydrogen bond. Now, this IR study may help to detect the presence of the conformer and this percentage of equilibrium. Let us consider ethylene glycol, where the two frequency absorption band of 3644 centimeters by 3612 centimeters in dilute CCl4 solution. As we need the dilute CCl4, the possibility of intermolecular hydrogen bonding is less. So we post that the molecule exists in the following two. One is the Gauge form, one is the anti form. So here in Gauge form, the hydrogen bonding is present, but in anti form the hydrogen bonding is not present. So obviously, so here for the Gauge form, the OH touching frequency is lower compared to the this. So obviously, the higher value of the absorption is for the non-bonded OH in the anti-conformer, lower value for absorption of the hydrogen bonding OH is the Gauge conformer. Now the difference in the two mu bar may be used to estimate the strength of hydrogen bonding. Higher the difference, higher is the strength of hydrogen bonding. Now the preferred conformation of the diastereomers of the glycerol of general formula respect to the one with the two hydroxyl group and Koch orientation as in stabilized through intramolecular hydrogen bonding. Thus, here we expect the following preferred conformation for meso and active varieties of basically. So here meso diastereomer and active diastereomer. If you close look on the above two conformations, we find that in the case of meso variety, the conformation of the two hydroxyl group are in the Koch to each other, but in the same time the two alkyl groups and the Koch to each other. Thus, there is a steric repulsion between the alkyl group. Where in the case of the active isomer, the variety of conformation of the two hydroxyl group are Koch each other, and the same time the two alkyl group and thus for the active variety, the above conformation is preferred one. But for meso variety, we expect the equilibrium between the following two equilibrium. So, and with the detection of the equilibrium will favorably determined by the bulkiness of the alkyl group. The following interference can be done by a study on the diastereomers of the given this glycol. So, with the increase, so here in the mesoprom, two are group in the two are group in the Koch conformation, so here the repulsion, so that will not favor this orientation by the active form, two are group in the anti-conformer, so this orientation is favored. So here these two mesodiasteromer has these two structure, so that's the steric bulk of the earth will identify the equilibrium of these two conformers. So with the increase of the bulkiness of the earth and the hydrogen bonding between the hydroxyl group and the hydroxyl group close to each other will be stronger in case of both diastereomer, and the hydroxyl group will be bending away from the bulky Koch alkyl group on the attraction carbon. As a result, in the bulkiness of earth, difference the structural frequency due to the unbonded and intramolecular hydrogen bonded hydrogen increase. So in case of mesoform, one hydroxyl group is Koch with one alkyl group in the configuration which the two hydroxyl group are Koch and to each other, while in the Koch case of active variety, both hydroxyl group are Koch with the alkyl groups with preferred conformer. Thus, the increase in the bulkiness of earth, hydrogen bonding between hydroxyl group will be stronger in case of active variety than of the meso variety. So with this increase in the bulkiness of earth, the difference in stressing frequency due to the unbonded and intermolecular hydrogen bonded of hydroxyl group will higher for the active variety than of the meso variety. So in case of meso variety, the increase with the increase of bulkiness are the percentage of population of conformation in which the hydroxyl group are Koch to each other and the alkyl group are Koch to each other will be decreased, and the percentage of population of the conformation in which the alkyl group are anti to each other and consequently hydroxyl group are anti to each other will be increased. Thus, in the case of meso variety, increase the bulkiness of R, the iron and intermolecular hydrogen bonded hydroxyl group will weaker or absent. So now we have the following data which are according to the above expression. So for the meso variety, the difference stretching frequency due to the unbonded and intermolecular hydrogen bonding the hydroxyl group in this molecule. So the active variety, when with the increase of the substitution, the stretching frequency is decreases, but for the active variety with the increase in the substitution, the OH stretching frequency, the difference between increases. Because here with the increase in the substitution, the stretching it favors the intermolecular hydrogen bonding. So that's why the stretching frequency difference is increases. So thank you.